Service Logic, we believe the future of the skilled trades lies in training and development. And that's why we created the Edge, a platform dedicated to empowering our greatest assets, our people. From hands-on training to leadership development, Edge is where technicians grow their skills, expand their opportunities, and build lasting careers. Because when people succeed, our companies, our customers, and our industry thrive. This is the Edge. This is the future of the skilled trades.
I chose the iConnect training equipment because I already previously had some iConnect training equipment. And I was very pleased with the equipment I had, the quality of it, and pre-designed labs that came with it. So when I expanded it more into the catalog, I decided I wanted to get this refrigeration trainer in my program to expand my program. My experience so far using the TU-155 has been a pretty good experience, especially my second year students. And it the light bulb kind of syndrome goes off when you see that little flicker in their eye and they're, oh, I got it. That's what us instructors, what we look for is the I got it moment. And this helps me to the I got it moment with my students, and that's what's my goal to achieve.
We are Daikin, the #1 global indoor comfort provider. Our innovative home and building solutions are engineered with energy efficiency and sustainability at their core, ensuring improved indoor air quality for all. From heating and cooling to ventilation, air purification, refrigeration technologies, and connected devices, we are at the forefront of technology, addressing the pressing challenges of sustainability.
Hello, everyone. Thank you so much for joining us once again on Did You Know, the ESCO HVAC show. Yeah, happy Thursday, everyone. Donald, great to have you here with us. Hadn't been on in a little while. I appreciate you spending some time hanging out with us. We've got Coldfinger joining in. Scott, yeah, I hear that we're getting a little snow in the Northwest right now. David Harrell, appreciate you joining us from Cincinnati. You're going to be getting some of that weather too. Katie joining us from Hillsboro, Missouri. Everyone, let us know in the chat where you're joining from. It's great to have you here with us, and yeah, it's really cool, Donald, to be able to have everyone here hanging out, getting to spend some time diving into our industry. Today, we're spending some quality time with our good friend Jim Fultz from White-Rodgers by Copeland. Jim, how's it going?
Hey, going great. Thanks for having me. Always a pleasure to be a part of this.
Yeah, it's a great time to dive deep into their industry, and I'm so grateful we've got Jocelyn hanging out with us. Jocelyn did not grow up in the HVAC industry, so we are just feeding her with the fire hydrant hose right now, learning about this industry and learning about all the cool things that are evolving and changing, but yet making sure that we're covering the fundamentals really, really well. And when we think about the fundamentals, sequence of operation is one of the most important things for us. Murph, thanks for joining us in Central Jersey. Paul Leonardi in Jersey. Also, he's on the south side of Jersey. James joining us from Florida. Grateful to have you all here. Well, when we think about sequence of operation, hey, Wayne, yeah, grateful to have you here. It's been a while. When we think about sequence of operation of a gas furnace, Jocelyn, this is a thing that often gets overlooked sometimes by technicians. Like when you go over, hey, that's right, Donald. Isn't it fun? Like I feel so honored to have, I feel like I have got a coworker and an apprentice all at the same time. Like when you walk over to the thermostat, it's cold, right? I'm actually, even though it looks like I'm in my studio, I'm broadcasting live from the ACTE conference down here in Nashville, Tennessee. It's pretty cold here, very cold in the Midwest. When we walk over to that thermostat and we want to turn on our gas furnace, like what happens? And even many technicians, they struggle to understand like the true sequence of how things are happening. Because if we can understand how something operates, we have a much better chance of determining the problem when they arise, because they will arise. Yeah, Donald, you're right. Sequence of operation, man. It's the key for everything. When we understand every sequence, well, then as a educator, we're going to be teaching that to the students so that when they become technicians, they literally are following the sequence to find the problem. If we know that if we start here and we know every little step along the way to the very end, then it's a matter of doing our math, following our sequence along the way. And when we stop, that's typically the component or the scenario of the component that is causing the problem. Paul, you get it, man. I know you teach this in everything. That sequence of operation is the most critical component. Now, when we went from, say, standing pilot furnaces into electronic ignition furnaces, everything started having timing sequences. And Jim and I had this conversation a while back, and he brought up a point. He says, do you know exactly how much time it is between each step along the way? And I'm like, I thought they were all different between the manufacturers. And he's like, maybe we should do a show on this. So Jim, let's start at the sequence of operation on a gas furnace so that it can help us understand exactly what is going on and what our controls are doing along the way.
Hey, you bet. So are we going to do this as a pop quiz all along the way?
I think we should. Yeah, because there's even been a couple of questions that you've brought up to me, and I've had to sit and think for a minute, because many times we might think we know what's happening, but do we really? Where did we learn that? Did we learn it from the correct education? And yeah, I think we should. I think we should allow the audience to do some of these Q&A for us.
All right. So the first question is, when the thermostat sends 24 volts out of the W terminal to the control board,
From the thermostat
to the control board, what's the first thing that happens? The absolute first thing that's going to happen when this control board receives 24 volts.
This is
on your chat, what you think it is.
This is a great one. So Jim, Garrett is joining us from Ivy Tech in Bloomington, Indiana, and his students are probably watching this right now. They join every week, learning from the top educators in our industry. And Donald, there you go. It's another one for you. This is going to be the pop quiz. What happens? We walk over to the wall. We got the thermostat. We turn it to heat. We turn the temperature up. And what is next?
Yeah.
I imagine Garrett's looking around the classroom. The classroom's going, "Oh, really? Going to put us on the spot for this?"
There you go. All right. Well, we ready to go, because if we don't, if we let too much time on these, it's gonna take.
We want him to get through it.
Second here. So first thing that happens, number one, 24 volts gets to the control board, and the control board processor checks itself. Number one.
There we go.
The processor is saying, "Hey, is everything okay with the RAM, with the processor functioning?" It's a self-safety test on the processor itself. So that's number one. And then we're going to go through a whole bunch of more self-checks before we actually have power coming out of that board. And when we get to that, we'll be ready for our next pop quiz here. Next thing that we're checking is we are checking the gas valve circuit. We are making sure that there's not 24 volts going to the gas valve.
Right.
Because if that gas valve's energized when we get to the point of the igniter starting and we've been blowing gas, safety issue. So we're checking the gas valve relay, making sure that it's open, making sure that there's no resistance,
no current
from the gas valve coil itself. And then after we check that gas valve, then we're going to go to the pressure switch circuit. and we're going to check to make sure it's open. So we're now not only checking the circuit board, but we're now checking another safety component. We're checking the pressure switch to make sure it's not stuck closed.
Very true.
Which, if it was stuck closed, then as soon as it got power would come back and say, hey, we got a good circuit here. So we're first checking the safety of the pressure switch, making sure that it is open. Then we're checking the limit circuit, the limit string. We want to make sure that there are no open limits. Those open limits would indicate there's another issue somewhere. And great point, Donald. This process is so fast for it to go through these checks to make sure everything is good. Only takes a couple seconds for them to be sending power out different places and making sure that is all happening. The limit circuit is good. The pressure switch is open. Power is now exiting the circuit board for the first thing to come on. Pop quiz. What's the first thing that comes on? And there's a comment here. Does an older 10 to 15 years old do that too, or just more modern boards? So we can go back once we get through this, and we'll talk about some of those old circuits and the way some of those old ones did, because this is more of what we're seeing today. In even the last 10, 15 years, most of what's out there is where that's at today. Once we get pretty much, I would probably put somewhere around 2006, which was the end of the smart valve era, when we had a separate controller and a valve that was running separate from the fan timer, and everything was going to an IFC. So I see multiple answers here that are right on the money. We are starting that inducer. So we've actually had that limit string verified, and we are now starting the inducer. The inducer is going to run, and it can take up to 6 to 8 seconds for that pressure switch to close. And once that pressure switch closes, then the next thing is where our next thing that's going to occur is our igniter is going to come on. But wait, it's not going to come on right away. We have a pre-purge time.
Purge delay. You bet.
Next pop quiz. Ready, folks?
Okay. All right. Here we go.
Does the inducer timing, which is industry standard for 99% of everything out there today, is 30-second pre-purge before we're going to turn that igniter on to do the igniter warm-up. Does that 30-second pre-purge timing start when the inducer motor starts, or does it start when the pressure switch closes?
Ooh, boy, that's a great question. We'll give it just a minute or two for people to chime in the chat. And so, Jocelyn, what we're talking about is once you've done that thermostat, that control board is looking for any failures in the safeties. And then it's going to make sure that there is no leftover fuel within the furnace from the last time it ran. So it's going to turn that draft inducer on, which is a motor that is pulling a negative pressure through the furnace, and it's going to be pushing out any exhaust gases out your flue, making sure that when we do get ready for that ignition, when we're going to try to start our sequence, that there's no leftover fuel within that furnace. We don't want that thing to go boom, because it had some kind of a malfunction. So it's an additional layer of safety on top of it. All right, so we got some answers coming in.
We do, and I see some right ones right there. When the pressure switch closes, that is right on the money. Our 30-second pre-purge is not when the inducer starts. It is when that pressure switch closes that we have verified that the flue is open, that there is no restrictions, and that pressure switch closed now starts that 30-second pre-purge. There are a few one-offs out there that would have different pre-purge timings on it, but for by and large, when we're dealing with standard residential equipment, most of what I've seen out there, all brands, all manufacturers, were typically at that 30-second pre-purge to be able to make sure that any raw gas has been cleaned out before we start that. So we went through the pre-purge. And now we are ready for what we call trial for ignition. And that trial for ignition is for a 120 volt igniter,
Mm-hmm.
17 seconds. We won't put that into a pop quiz, but we will put, while we're talking about it, the 80 volt igniters, which were
Yes.
some of the early igniters that were out there. The 80 volt igniters had a different warm up time. Can we get some answers in our chat? What was or is the warm-up time for an 80 volt igniter versus a 120 volt igniter? So the
Ooh.
120 volt igniter is what we're working with today. Originally, there were two manufacturers, major manufacturers that started out with an 80 volt igniter, and from what I have researched, the understanding of that was we have lower voltage. Typically, if we drop our voltage down, we can actually get longevity out of a device with a lower amount of voltage. And so we added additional resistors and circuits in there for that 80 volt igniter to be able to drop that voltage from 120 down to 80.
Mm-hmm.
But then we went back to 120. We didn't leave it at 80.
Right.
And it was like, well, so was that a cost cutting measure? Manufacturers were like, hey, how do we drop the price of this board? Let's get rid of those extra resistors in there and just leave it flow 120 volts straight through. No, that's not why we switched. So let's go back to our answer. 80 volt igniters. Standard 80 volt igniter warm-up time is 23 seconds.
23. Okay.
3 seconds.
Donald, getting closer there. Donald was 30 to 45, but yeah, 23, because it's going to take a little bit longer for that lower voltage to be able to get up to its heat potential.
So if you're running an igniter 23 seconds every time you warm up that igniter versus you're only warming it up 17 seconds, which one's going to last longer?
Right.
So we went from 180 volt to 120 volt, not because it was cheaper to run that, but because we actually could extend the life of the igniter by having a less amount of time that we were running that 80 volt igniter. Now, so there are some other timings out there on some igniters. There are some one-offs. There's what I call the Norton Mini, which is a very small igniter, and if you run that thing more than 4 seconds, you'll fry it.
Yeah.
So you have to know what igniter you're having out there, and what I'm discussing right now is more of an umbrella of what the industry standard, what you're seeing across all of your major residential gas furnace units that are out there. 17 seconds for the 120 volt igniter, 23 seconds for the 80 volt igniter. And again, those can have a little bit of fluctuation between manufacturer, but that's pretty close to what you're going to see across the board on all of those. Once you get to the point that igniter is warm enough to ignite gas, our next step from that is to open up the gas valve. So the gas valve opens up with that igniter glowing. How long do we have before the control board says, I didn't see the flame, and shuts off?
Very good question. We'll definitely leave a minute or two for people to enter that into the chat, because that is one that I have heard so many different reference points before. And so, yeah, we'll take a second, allow that to come through. And Hugo, that is such a great question. And we're going to go through this whole sequence of operation. If we have time at the end, we are definitely going to give you some things to look at for that, because you're the reason we do this show. We are here to help our entire industry understand the things that we work on better. So we're grateful that you joined us. And yeah, we have enough time. We will spend a little bit on that. So Jocelyn, what we're talking about is, all right, so we turn the thermostat on. Our control board has went through some safeties to make sure that it's okay to start the procedure. We've started the procedure. We've turned on this draft inducer to make sure that we've pulled out any of these potential flammable gases that could still be in the heat exchanger. We went, okay, we're good. So we've closed that pressure switch. We've got good flow coming out of our flue pipe. We started up the igniter, which is we're going to create a hot surface for our gas to be lit, to be ignited. But we want to make sure that we're doing it safely, because what if there's a problem? So from the time that we turn that gas on and we allow it to flow across this hot igniter, it should light pretty quick. And if it doesn't, we know that we got a problem. But how much time is that? So in the chat, we've got quite a few. This is why we like to talk about this. Is it 3 seconds? Is it 5 seconds? And let's dive into that, Jim.
Yeah, no, great answers. And the 3 to 5 range, you're dead on, because it can vary a second or two there. But 5 is what we're going to see as the main, or the maximum, that we're going to let gas flow into that heat exchanger without seeing that flame. So great answers, everybody. You're right on target. 3 to 5 is a great number there for you. There are some boards that'll say 4 to 5, some that'll say 3 to 4, but usually that's your range right there. The 3 to 5 is great answers. And going back to a comment I saw there earlier about the different type of igniters, and we can address that here really quick. The early igniters were made of silicon carbide. They were very porous. They were very brittle. They are still manufactured. They're still available out there today. If you are buying a silicon carbide igniter, we always recommend, before you even leave the supply house, that you open up that box and you make sure that it's intact before you get it. That is how brittle they are, and they can break super easy. With their porousness, they also have the ability to absorb any oils from your hand.
True.
When you put oil on something that's hot and glowing, that oil heats up and it breaks down the material faster. And so for silicon carbide igniters, it has always been recommended, don't handle the igniter itself with your hands, your fingers, your hands on that oil will be absorbed and shorten the life of that silicon carbide igniter. Silicon nitride, on the other hand, very dense material, very hard to break. And that is what we have switched to. Pretty much everything that we have manufactured new out there are the silicon nitride igniters. And with those, if you touch them, the effect on them is going to be very minimal. I always say, just make a practice of not touching them. But for the sake of the argument, if you happen to, more than likely you're not going to see any difference with that silicon nitride igniter, because the denseness, the lack of open pores or open holes in that igniter. So that is a transition also that occurred. The early igniters, silicon carbide, 80 volts, and then we slowly switched to silicon nitride at the same time that we were switching over to the 120 volt igniters. One final piece that I want to add on that within this sequence of operation and troubleshooting, if you've ever been out to a furnace and you found a bad igniter, you pulled it out, hey, it's an 80 volt igniter, you went out to the truck, grabbed another one, put it back in. I need to double check. Let's look at the furnace model number. What did this furnace get made with? Well, you cross-reference the model number of the furnace. It's an 80 volt igniter. Hey, you're good to go, right? Right? Or are you?
Good question.
When you're replacing an igniter, always verify the igniter voltage on the board, not by the furnace, but by the board itself. Because the furnace may have originally been an 80-volt igniter furnace, but if someone upgraded the board and they failed to upgrade the igniter at the same time,
Great
that
point.
could be why that
Igniter.
80-volt igniter that got 120 volts uh, didn't last very long. Typically,
Exactly.
you won't get a whole heating season out of an 80-volt igniter that's getting 120 volts. And that's not job security, that's upset customers. So double check, always double check what the voltage for the igniter should be on the circuit board itself. So
Absolutely.
we have went through, we have went to that 3 to 5 seconds and proved that the flame is there. At that point, the igniter is going to shut off, the gas valve remains on, and you are in your call of heat. That is your process of the starting of a furnace. And if you understand that, that is going to make troubleshooting so much easier. Because what if the inducer comes on, you hear the pressure switch click, which you should be able to hear that, and then nothing else happens? What's potentially the issue with the furnace? If you know the sequence of operation, after that 30-second pre-purge, the igniter should be glowing. But if the igniter is not glowing, that's where you're going to look. So knowing the sequence of operation, knowing what should be the next thing is beneficial. Also, from our perspective, knowing those timings, keeping those timings in mind as you're going through that, and even timing them. Hey, it's been a minute and a half, 2 minutes, and the inducer is still running, but nothing's happening. What's going on here? It's too long. So knowing how long things should be occurring is very beneficial as you walk through that process.
Yeah, thinking about those timings, there's a lot of different opportunities to have timings that could be potentially off. If we have a furnace that has had had multiple igniters replaced in a short period of time, and we're looking at it and going, boy, something's going wrong. What's going wrong? And then we actually follow that sequence and realize, well, maybe it's the fact that a timing sequence has somehow gotten off on this control board, and this igniter is now running for 45 seconds, 60 seconds, 90 seconds, much longer spans than it was designed for. It will cause that premature failure of that igniter. And I have seen those before. So understanding the timing will help us understand, is the sequence being followed properly?
You bet. You
Yep.
bet. So that whole process, from the time there's a call for heat to the time that there is flame in the furnace, is less than a minute.
Wow.
And so when you're observing this, things are happening pretty quick. Things are occurring, and I do have my simulator here with me today,
Nice.
Clifton. So if we're ready, we can make a simulated call for heat and actually watch those things as the control board is initiating them.
I think so. Jocelyn, we put a teaser out in the thumbnail. I think this is a great time to introduce that to everyone. For everyone that is joining us, White-Rodgers by Copeland has actually given us the opportunity to acquire a free shop light simply by filling out the form to be able to get the information and where to get it to you. And you'll also in that learn a little bit more about the control board that we are getting ready to discuss on this trainer. It's a fantastic board, has a lot of information. It has the whole flame rectification process, which we may spend a little bit of time talking about, because that is one of our final components of that sequence of operation. Like, how do we determine that the flame is there and that there is enough? So yeah, we'll leave that QR up for everyone to grab. We encourage you to fill that out. And let's talk about this simulator a little bit, Jim.
All right. Well, I will switch the screens over here. and place it front and center here. And the example that I have today is with our White-Rodgers 50M56X 843, which is our most universal control board out there. This control board has multiple terminals on it, and it crosses over 550 different boards,
Nice.
or different SKUs, part numbers. And so a nice truck stock item that allows you to repair while you're out on the job and not have to run and get something. So let's go through that sequence of operation here and actually watch as it occurs. And we're going to do that. I have my app on my phone here, so we're going to be able to turn that temperature up. In the app, it actually will change colors, and we'll see that change and make that call for heat. And while that's doing that, we have the limit circuit. It's going that quick. The inducer started, the pressure switch closed, and that pressure switch closed is now giving us that
Pre-purge.
30-second pre-purge time where we are making sure there is no raw gas in that heat exchanger, that everything is free and clear, and we're good to go. So this is the longest part of this process is that 30-second pre-purge. Once we get past that 30-second pre-purge, then we will initiate the igniter warm-up, which the hot surface igniter, and we actually have to see on the board itself, it tells us what's going on with the igniter warming up. And that igniter warm-up is 17 seconds. Now, this board actually will back that off a little bit if it has a good instant fire and go a little quicker. Once we have the gas valve on, we see the flame senses saw that flame almost instantaneously, and the gas valve went off. So we are now in a live fire with this. Everything is functioning. The limits are all closed. The inducer's running, pressure switch is closed, gas valve is on. And one cool thing about this board is it actually flashes between telling you that it's in the heat mode and the flame current right on the board. So you see the flame current right now, we're showing 1.2, not a super strong flame current. But I would stop here right now and just simply share that the direct ignition type of application in furnaces first came out, was first introduced by White-Rodgers. We were first to market with it, the initial patent to do that. And so we understand what it means to have good flame current, and we actually have controls that can read some of the lowest. And we're going to turn this dial here to our weak setting, and we can actually see this. We have got it fooled to going down. We typically will tell you it will read down to a half a microamp, and we're actually showing a little bit lower than this on this board, and it's still running. If we drop below that, if we go all the way out, then we lose our gas valve, and we go into a purge cycle again to try and relight, because it's not a imminent danger that we can go ahead and retry relight. That is what it's going to do, is going to go through and relight. And when we see that, then we can pull the flame sensor out, we can clean it, we can go through, we can replace it with one of the nice White-Rodgers universal cuttable bendable flame sensors, and we do that. We get that new flame sensor in there, and we're going back through. Hot surface ignition ran for its 17 seconds. The gas valve came on, and we're back in fire with a clean or a replaced flame sensor. And look at that, we got a flame reading of 4.0. So most of our universal boards have test pins that 1 microamp equals 1 volt DC, so you can test that yourself there, or you can do it the old-fashioned way of pulling the wire off of the back of the flame sense rod and putting your microamp DC voltage or DC microamp meter in series with that to read it that way. But you don't need to with this. It's actually right here on the board giving you what that flame current is. So
Love it.
full sequence of operation. We also would have the fan that would come on, that would time on. That is a variable. Every furnace does have options with that. Most manufacturers are going to have somewhere around 4 different timings that you can adjust depending on the comfort level and how much heat that heat exchanger is holding when the heat or the gas goes off. And typically the range goes from getting the last drop of heat out to be the most efficient to shutting off before the air starts feeling uncomfortable for the homeowner. So that's a variable that can be set. The longer you allow it to run, obviously the more heat, even though it may not be comfortable coming out of the registers, you're going to get the more efficient you're going to have that. So there's a balance there to get to wherever that's at. So we can end that call for heat, and in that ending of that call for heat, it's going to shut the gas valve off and go through the post purge, and we'll see this heat PO or post purge. So our board's telling us exactly what's going on, and we can see that occur. Our inducer will run for the post 25 seconds post purge, which is fairly common standard in the industry. Could have had a pop quiz on that. Sorry.
Yeah, that'd been a good one too.
Let the cat out.
That's all right. Oh, we got some other. I got one I want to bring up here in a minute.
All right. So we've shut off the inducer after our 25 seconds, and now it's just a matter of the fan shutting off after the timing is finished on that. So all of those settings as far as the fan timings, and you can actually adjust the inducer timings. Do you need to? Typically, your pre-purge is going to be 30 seconds, your post-purge 25, your inter-purge is usually 60 seconds. You can see those if you're wanting to know what those are. This control actually has NFC capability where
near field.
You can hit the NFC. Let's go back and go do this from home. I already had this open up. So connect to control and ready to scan. We're going to put the front of the phone over our scan area here, and we have the ability to adjust our blower selection, your heat on off delay, and then cool on off fans. These timings for the purge can be adjusted. But again, unless you have a furnace that you know is something unique, those shouldn't need to be adjusted. This board also has the ability to clear the harness configuration. So with this harness, these two harnesses this simulator was built with these two. It's simulating a Goodman furnace. We could do a train furnace here towards the bottom plug, or a carrier ICP in these upright pin connectors. So there's no harnesses with this. You simply plug and play. The board knows what's going on. So how does it know what's going on? Well, let's go back to that sequence of operation.
Right.
And we can actually clear the harness configuration on here. But before I do that, I like to hit reset default settings and then clear harness configuration. And these are really beneficial, because if you put this board in and a couple weeks later you replace that piece of equipment for a homeowner, now you have a board, and this board is
Universal service board.
This specific manufacturer, well, unless you run into that specific furnace again, are you going to be able to use this board? Well, if you reset default settings and clear the harness configuration, and we're going to turn the power off to do this, update the control, and we'll read this and write an updated control. We have now updated this control to factory. It is now back to the way it came from the factory. And with that, when we power this up, this is what happens with this universal board when it first starts up. And knowing sequence of operation is so beneficial, because you know different circuits and where they're at in the furnace and how they function. This board will first send 24 volts out of these different pins on the pins that would potentially be the limit circuit.
Oh, right.
And they're going to look for 24 volts coming back to that limit circuit. And so whichever one of these has that 24 volts return, we know our limit circuit is there and we know where
Right.
it's plugged into. Then it's going to go up into this area of the board and it's going to send 120 volts out of the different pins that could be the igniter. It's going to look for the igniter to come on. And this igniter is only on long enough to see resistance. You will not even see the igniter glow when it's doing this test. Once it knows there's resistance on this circuit, that's the igniter, it goes to the other 120 volt circuit on that specific pin that it's on, and it starts the inducer. The inducer starts up, and it goes back to the pin that had the limit circuit on it, sends 24 volts out where the pressure switch circuit should be,
Right.
and it's going to look for that pressure switch to close. Once that pressure switch closes, it's confirmed 2 high voltage circuits, 2 low voltage circuits, and knows exactly what it's plugged into. So let's watch that happen
I
here
love that.
in real time. We're powering things on, and we're going to see it check the limit circuit, the hot surface igniter that quick, and it's turning on the inducer. And after the inducer is on, the pressure switch closes, it verifies the pressure switch is closed, and that quick, we are in standby mode. That's
That's
all
crazy.
it takes. So what happens if the inducer motor failed? What happens if we don't have an inducer or the pressure switch circuit or the pressure switch itself is bad? We go to power it up, and it's going to check the limit circuit, the hot surface igniter, the inducer, not coming on, which means our pressure switch isn't going to close. It's going to look for that pressure switch to close for around 15 to 20 seconds. It doesn't see a closed pressure switch, and we get it
Our fault code.
error code,
Look at that.
harness configuration error. So we do get this board back from time to time, and somebody says, "Hey, I got a defective board.
All right.
What did it have on it? Oh, I had an E41."
Right.
Did you happen to check the limit circuit, the pressure switch, the inducer, and the igniter? Are you confident those 4 circuits are good? Because if they're not, this board can't do its thing. So if those 4 things are good, when you go to power it up, it's going to check those 4. How many times does it do that? Does it do it every time? No. Does it twice? Once when you have the door switch on the furnace and you're doing your commissioning testing, you take your safety cover off that door switch, put the actual door back on, and 2 times it is powered up. It's went through the process and it goes to on or standby, and at that point it's locked in. It will not go through and check to see what harnesses is configured after that. So it will be able at that point to detect and give an error code should the limit circuit open up, should the pressure switch not close, or the pressure switch be stuck closed. It's going to be able to identify those because it has locked it into that specific model and
That model, that type.
Yep. Yep.
That's brilliant. I've worked with a lot of universal controls in the past, but that is a game changer. Yeah, Donald, you're right. That is quite the incredible technology, and it's a great troubleshooting setup that you have here for this. When we look at the sequence of operation, this really is such a helpful device, not just for the troubleshooting, but even as an educator in the classroom. One of the things in there that I've spent an entire class on before, and so we're just going to talk about it very briefly. For me, one of the most important parts of operation is understanding what that flame rectification is, and you're actually displaying it right on the control. It has its own sequence of operation that's critical to understand, right? We are going to, when we get to that point of verifying flame, we're going to apply voltage to that flame rod that is going to jump across the flame. It's going to create a rectification of that. It's electricity. It's trying to find its way to ground. It's going to make its way to ground. And in the process, we have put a load on the flame. And that's where the microamp comes into play. We are actually putting a load on the flame. So in that sequence, we think, okay, we're applying power to the flame rod. It's got to go through the flame. It's got to make its way to ground, which means it's going to have to connect to a surface. On the display, we can actually now see what is our microamp reading. Like Jim mentioned earlier, if it's low, we go to clean our flame rod in case it had oxidation built up on it. If we didn't get enough of our load being able to read across the flame, we can actually clean the surface of the burners. We can verify that our ground screw is making proper contact. And in the process, we're actually monitoring, once we refire up, what is that amount of current being applied to the flame. I love that, not just for the servicing side, but as an educator in a classroom. It's perfect as an example.
And I like the second way that you described that. Your first comment was the electric jumps across the flame, and the second description you gave was it rode across the flame. And that's really what's going on, is this current riding across the flame. Well, how's it doing that? Well, to try to break it down to as simple as possible is I have a joke that I probably botch every time, but I still like to tell it, that the two atoms are walking down the street, and one atom looks at the other atom and says, "I think I lost a neutron." And he says, "Are you sure?" to his friend. And his friend says, "Yes, I'm positive." and that is exactly what's going on. If you got the joke, you're on target to understand flames. Fancy words there.
Yeah.
What's happening is you have that gas going into the front of the burner where it's igniting, and those atoms are splitting up and going around in different areas of that flame, being sucked into that heat exchanger to be pulled through. And while they're floating around, the positive ions are actually touching that flame rod, and they are flowing, those positive ions are flowing with that current back to the burner, touching the burner, and the burner's ground.
Yep.
And it's grounding out. And so the board is reading resistance on that electric that's going out that flame rod. Now, if you touch that flame rod when it's live, without the flame around, obviously, will it shock you? You might be able to feel it, but remember, we're talking microamps. It's less than 1 amp that's in that. It still has the potential to tingle. I can't go.
Don't recommend it. Not the best example to use in the classroom. Hey, kids, stick your finger over here.
But let's look. This kind of opens up one more point that I really like to hit home with in helping overcome the universal hurdle, and that is, aside from a blower that's got a neutral and a whole bunch of power wires on an old PSC that's different fan speeds, everything else going into that circuit board has pairs. All the wires are pairs. And you say, well, wait a minute, what's the pairs? Well, let's go back to this board here and let's look at this little group of wires here. And I can peel them off because I know mostly what they are. You got a pair that's going to the gas valve, 24 volt and common. You got a pair that is the transformer coming in, 24 volt and common. You have a pair that's the limit circuit, 24 volt going out, 24 volt returning. It's a circuit, it's not a load. Same way with the two purple ones for the pressure switch. And then finally, look what's left, green and orange. Well, orange typically is going to be your flame rod. That's that voltage. And by the way, it would read anywhere from 80 volts to 180 volt is your typical voltage. AC voltage is going out AC that's going out to that flame rod, it's rectified through those positive ions taking it back to the burner. Those ions only can take half of the sine wave, so the other half is lost, and that turns it into a DC signal. The other wire that we have here, green, where does that land?
Wait a minute. Is that a dedicated part of this circuit?
It is every time in almost all of your furnaces today, you will find a green wire coming off the circuit board going
right to the burner box.
Screws that hold the burner manifold onto the burner bracket.
Yep.
That green wire underneath that is that ground, so that this orange wire can see that grounding back at the control to see that that flame is present. So Paul, great comment. Having a good ground is absolutely important. When you don't have a good ground, that you're messing everything up within that control. It doesn't see that. Earlier boards, and I do want to, we got a couple minutes left. I want to talk about earlier systems here a little bit.
You bet.
Earlier boards would not be able to identify when the hot and then going to the board was reversed.
Polarity, yeah.
Yes. Will the board turn on? Yes. Will the inducer turn on? Yes. It's alternating current. It'll work. But what happens when you reverse those two wires is the orange wire with the flame sense probe going in front of the burner now has 0 volts on it.
Right.
It doesn't have 100.
Becomes ground.
80 to 180, and so ground can't ground itself out to ground, and that furnace would not see the flame present. You would have trial for ignition. The flame would come on. About 3 to 5 seconds later, the flame goes off, and it's like, oh, did the pressure switch close because there's a slight restriction somewhere? What am I looking for? And it could be a real head scratcher, but the reality is, if you're shutting off between that 3 to 5 seconds, you had a reverse polarity on that board. Most of your boards today will recognize
that.
Will see that reverse polarity and give you an error code saying, hey, you need to reverse your wires.
Right.
And let's go back to a couple more things that I wanted to mention in sequence of operation. We talked today about what we see today as more standard. If we go back to that pre-2006 era, where we had different types of controls. We had a fan timer that was separate from the igniter circuit, or whether it was a smart valve or a hot surface ignition or a spark ignition. There are times that the pressure switch was in series from the control board to power the gas valve. And so if the pressure switch never closed, the 24 volts never got to the gas valve to turn the gas valve on. So there are different sequences of things that occurred in earlier types of furnaces that do not follow exactly what we shared here at the beginning today as far as that exact sequence of operation. There's additional circuits that were built into some of those earlier controls that are nowadays pretty much standardized throughout the industry on your furnaces.
Boy, Jim, we really appreciate that. That clarifies a lot of our sequencing, a lot of our operation. One day, Jocelyn is going to get a call from one of her family members and says, my furnace ain't running right. She's going to say, what's it doing? Tell me the sequence of operation. It lights, and then it retries. And she's going to say, shut it off, let it cool down. Go follow that orange wire, clean that rod. Call me back.
You betcha.
Jocelyn, if you don't mind, could you copy that link to the free shop light and put that into the chat for everyone as well? I wasn't thinking there might be people joining us from a mobile device and not able to scan that. So we can put that in as a link for everyone. We'll also put it in the description of the video once we're done editing as well. So we encourage you all to go over and check out this board, fill out the information, get yourself the free flashlight. I did myself. Looking forward to it. Looks like a really cool piece.
It's very long.
Yeah, it's a pretty good link. Anyone have any questions from the chat? Anyone have anything that they would like to dive a little bit deeper into? I know we did have that question earlier on from Hugo. And Hugo, I'm hoping that as we have completed the sequence of operation, it has become a little bit more clear to you on that sequence. Now, one of the things that you had mentioned that you had replaced the pressure switch and you were still having some issues along the way. Once we get to that point, then it's a matter of making sure that we have proper airflow through our exhaust, making sure that using a manometer to check the pressure coming off from our draft inducer going over to our pressure switch, and also making sure that we have not allowed condensation to trap in the tubing from the draft inducer over to the pressure switch. Happens very commonly. So there are a few other things that you can check there, but overall, it sounds like sequence of operation was being completed, but something was breaking the sequence, and that is what we start doing. And when we get into the technical side, we follow through till we are losing that sequence, and then we know, okay, if I'm losing my sequence here, is there something that is causing my sequence to be broken? And that's when we start getting into some of the mechanical troubleshooting. Like we're following the electrical sequence of operation. If my electrical sequence stops, it's probably because I've had a mechanical operation, either from a piece of equipment, from a component, or from an environment. Things like ice building up in flue pipes and water collecting in places that it shouldn't be. So a variety of things that we can look at. But when we follow that electrical sequence of operation, it's definitely going to get us where we need to be.
So let's close that a little bit more here with just kind of reinforcing what you're sharing there, Clifton, and that just simply is, how do we troubleshoot? Well, when you saw our control here today, you actually saw with lights what was going on.
Right.
You can actually see that happen. When you are in the front of a furnace, you can see when the shaft of the inducer starts. You can hear when that pressure switch closes most of the time. You can see the igniter start to glow. You can hear the gas valve click. So your troubleshooting starts out using your senses, just by observing and watching, seeing where in that sequence of operation that it has stopped. Now, back to that question of the pressure switch, you was able to see and look and say, okay, this is where it appears that issue is. But if you're not measuring, at that point you're guessing. And so we use our common senses, our hearing, our sight, sometimes our smell. If we got a carbon monoxide issue, we walk in and we instantly know, hey, we need to open some windows here. Those are things that we can tell by our senses. Then we go and we pull out the meters, and the meters is what we use to actually confirm things. And so the question that was raised there, I had a pressure switch, I replaced this pressure switch, and I got the same error code. And my question back to you would be, did you put your meter on voltage and touch each side of that pressure switch before it closed? You should have got 24 volts because you was on two sides of a circuit. As soon as it closed, it's the same voltage going through and your meter would go to 0. Did you confirm that the pressure switch was closing or not? Because your meter is going to tell you for sure whether it's closing, and if it's closing, then more than likely you're not going to get that error code. So I would highly suspect that even though you changed the pressure switch out, you could have still had an issue, and without checking with the meter to see if it was closing or not, there's no way for us to be able to take another step of diagnosing that, with the exception of not only do you check the pressure switch, but where the hose goes into the furnace, there are times that you can have buildup right at the inside of that port that can restrict that pressure switch from pulling that negative pressure and causing that issue. outside of the pressure switch itself. So there's other things that can be checked to just kind of do a little online troubleshooting here with that.
Love it. No, thank you so much, Jim. I mean, that's really what we're here to do, is to, to help guide and advise our industry. One of the questions came in from Paul Leonardi. What is the part number of this board? I know, Paul, you're probably liking this thing as much as I am. That QR link will actually take you to a page that has information for this particular board, as well as the form to be able to get the free light that goes along with this same promo. So yeah, definitely want to go check that out. I'm curious myself, Jim, is this trainer going to be something available, or are you just you hoarding this to yourself?
we are in the process. We've had multiple requests here in the last year, and we're in the process of getting the schematic put together for it, and the parts list for all the parts in it.
Very cool.
It's just a toy that I built to be able to share with the industry, and there is potential for this to be something that will be readily available from Copeland here in the future for anybody to use, classroom or any type of training you want.
Very cool. Yeah, beautiful trainer. Really appreciate you sharing that with us, diving into the sequence of operation and the timing components of that, and troubleshooting as well.
Yep.
So I thank you all so much for joining us again this week. We're grateful to have you all here. We're going to be having some holidays coming up. I encourage everyone to spend some time enjoying a little bit of time away from work, time with family. We will still be doing the show. We're going to have a variety of new learning opportunities coming your way. Jocelyn and I have been out doing some behind the scenes video shoots. We have so many new things to share with you in the next few weeks and few months. So encourage you all to join in with us. Make sure that you go check out the board from White-Rodgers by Copeland. Use that QR link to learn a little bit more about it. And I think we're going to wrap it up.
We you just reminded me. I'm looking at the chat here. One final piece. We're gonna go back to our screen
All
here,
right.
to our phone, and that is WR Mobile.
Oh, that app.
In here.
Yeah.
Saying, yeah. What's the part number of the board? So you go to WR Mobile. When you click on that, you can go search by part number. You can put in your part number that you have, and this part number can be a White-Rodgers part number, an OEM part number. It can be a old part number that's obsolete, and all you got to do is start typing in a number, and once you do that, and you less is more. If you put the whole thing in, if you don't have the dash at the right spot, it's not going to see it. So usually I say 4 or 5 digits, hit search, and you have what board that you're talking about shows up. You tap that board that you actually have, and voila, there you are. You have the 50M56X that one crossed over to.
Nice.
And within the app, there's an install video you can watch. The installation instructions are in there, spec sheet, all of that data is readily available right inside the White-Rodgers Mobile, the WR Mobile app, to get you everything nice and quick and easy. So that's your go-to to be able to do any cross-referencing to see if our controls, our universal controls, will do the job for you and allow you to repair while you're there.
Man,
and fantastic
add-on.
I'm all done, Clifton. Thank you so much.
Oh, this is great.
It's been a pleasure. We have thoroughly enjoyed being able to spend some time here with you today, and thanks to everyone who joined us online as well. I appreciate it as well.
Same here. We always have a good time helping teach the industry. I am always learning something from you, and I encourage you all to connect with Jim on LinkedIn, learn about the trainings that they're doing all over the place. He is a very, very busy person, as well as the rest of the team with White-Rodgers and Copeland. So we thank you all for joining us, and we will see you all again next week on Did You Know, the ESCO HVAC show. Bye, everybody.